basis. And Bronsted Lowry is really an updated version. It's one step up from Arrhenius' definition. Arrhenius had the idea that, again, you had something like HCl. And when you put HCl into water, the HCl broke down, of course, forming a H plus ion and a Cl negative ion. Something about this H plus ion. First of all, we're going to start calling this a proton. And the reason why we call it a proton is if you look at standard hydrogen as an atom. Oops, undo that again. Sorry. If you look at hydrogen as an atom, it contains one electron. Hydrogen also contains one proton. If hydrogen loses this electron, then of course the electron is gone, the outer shell is gone, so all you're left with is one proton. So one proton and H plus are the same thing, because obviously when it loses the electron, it becomes H plus. So from now on we'll be calling H plus as protons. This was the Arrhenius model of doing things. Arrhenius, there was a slight problem with this, because H pluses, when they're in solution with water, they don't exist independently. So what was happening was the H plus here was reacting with the water molecules. These two things were reacting, and they were forming a thing called a hydronium ion, which is H3O positive. Now, your basic reaction for this one here will be written as this. This substance here is called a hydronium ion. Now, the difference here is Arrhenius was looking at this idea, and he was just looking at how things dissociated in water. He was only interested in the actual HCl, how it dissociated down into these two things. Whereas Bronsted and Lowry came along afterwards, and Bronsted and Lowry were more interested in when it dissociated, what happened to the proton. And what they found was these protons ended up being donated to other molecules, and they formed something new. So in this particular example, when the proton was in the water solution, it doesn't exist on its own in water, so it reacts with the water molecule, forming this. So Bronsted and Lowry came up with an alternate definition for an acid. And they said an acid was a proton donor. If you donated protons, you were an acid. They came up with the opposite then for a base. The base was a proton acceptor. Obviously, if something is donating a proton, something has to accept it. In this particular example here, where's this H plus coming from? This H plus is coming from the HCl. So the HCl is donating a proton. So that will be an acid. What's accepting the proton? This particular water molecule here, H2O, is accepting this proton. So this one here is going to be a base. Let's look at some more examples of how that works. So working off these, let's have a look at something like this. So we've got NH3, which is ammonia, and you react it with water. And what you find is you end up forming NH4 positive ions in solution, and you get OH minus ions. So now what we need to do is we need to identify what's happening here. Generally the way I do this is I look at my products and I try to figure out what way the hydrogen is moving. Now obviously we have NH3 on the left, and on the right hand side it ends up becoming NH4 positive. So somewhere along the way this has gained a H plus. where's the only place it can gain it from? It gains it from here. Remember, these two molecules are reacting. So the H plus actually moves from here to here. So H moves from here to here. That makes sense because NH3 ends up becoming NH4 positive. So it increases by a H plus. But the other side of it is true. If this is H2O and it's donating a H plus, when it loses a H plus, it goes down to a H and an O, which is this one here. So that makes sense. So what we've got here is this movement from here to this side is donating. Now, if something donates a proton, it's called an acid. And that's written up here. So in this particular example, this is an acid because it donates a proton. This thing here, NH3, this accepts the proton because it ends up becoming NH4 positive. If this accepts the proton, according to our definition, this is then a base. If you look at the simple example that we had earlier on, which was HCl plus water, which is H2O, this forms H3O positive and chlorine ions, Cl minus. Again, same thing with this. What's happening here? Well, you start off with HCl, and you can see it becomes Cl minus over here. So it's obviously going to lose a H somewhere along the way. If it loses it, it has to give it somewhere. You can't just let one thing go and not add it on somewhere else. So what happens is the H leaves the left-hand side from the hydrochloric acid and it joins on the H2O. You can see the arrow is moving in a different direction here than this one. It's the HCl that's donating this time. And again, does that make sense? H2O is here. On the right-hand side, it's H3O positive, which means it's accepted it. So over here, if HCl is donating, then HCl is the acid. H2O is accepting the proton and becoming H3O positive. So that means this is the base. And there's two examples. So this is your Bronsted-Lowry idea that an acid is a proton donor and your base is a proton acceptor. Another thing you might have noticed here is your acid and your base in these two examples. In this particular one, water is acting as an acid, and in this particular one, water is acting as a base. And that's perfectly acceptable. Substances that can act as an acid and a base are called amphoteric. So amphoteric substance can donate and accept protons. It's weird to think of water as an acid or water as a base, but again, we have to think about it in terms of whether something is donating a proton or accepting a proton. Definition was Arrhenius only occurred in water, which left us with a problem with this in chemistry. So let's say you had something like this. HCl plus ammonia, which is NH3, and that produces substance NH4Cl. And again, Arrhenius couldn't really explain this one properly, whereas Bronsted-Lowry's idea does. And as you can see here, what's happening? The NH3 is becoming NH4. So there is a donation. Okay, you've got the H leaving here and joining on here. Because this is donating, you end up with HCl being an acid. NH3 is going to accept it, so this becomes a base. And then that forms that substance. That's it pretty much for Bronsted-Lowry acids and bases. The only thing that you've got to know is if an acid is a proton donor and a base is a proton acceptor, well then what happens, I'm just going to select this for a second and copy it, and hopefully it'll paste down here. It will, fantastic. So what happens if you are a strong acid? What happens if you are a strong base? Arrhenius said that these are things that completely dissociated or almost completely dissociated. A strong acid, very simply, is a good proton donor, and a strong base is a good proton acceptor. And then on the other side, you will also have the opposite for a weak acid and base. So a weak acid and a weak base. And this one here is going to be a poor proton donor and poor proton acceptor. And that ends the Bronsted Lowry video.